Now we will see how the frequencies, filters when they are applied changes the data. This is a very important topic. So maybe this will help you use these filters appropriately. So filters are both good and bad in the sense that the use depends on how intelligently you use the filters. So until now, if some of you who are following it along with me need not do this, you can just view this and that would be sufficient. We have a small package that comes along with the installations dipole simulator, and I don't think this comes with the latest version. So here you can see when I change the filters, what happens to the data. So it's not that there's no filter which is an absolute filter that just cuts off what you want and then gives you the data. There's no filter like that. But you can also view. So then first I want to do a simulated I want to load a data in which you can see the auditory input has been simulated. Load model file. So now I will go to Home. Go to C drive. Go to C drive. And there I go to program files. This is the model. I go to sorry, not here. I go to C drive. I go to public, users, public, documents, public, then BESA 7.1 examples. Here I have this learn by simulations folder, and here AC 2D biphasic synchronous data. So as you can see, there are two sources, two dipoles which has been simulated, and both are simulated over the auditory regions. If you can look at it, you should be able to know that. And the red and blue dipoles are there in the data. Now, when I apply the filters, I wanted to see what happens to the data, real data. Now, suppose this is the real data. I want to introduce the filters. Edit filters. And now, so please know that this data comes over the frequency of around 5 hertz. Okay. So let me just keep the high cut at 30, which is far away from it, and low frequency at 1 hertz. Now you can see that there is a gray. Let me just drag it. So the red waveform which you see on the top shows you the actual simulated data. And the gray, if you see this gray, do you see this gray? Are you able to see this? Yeah. Okay, thank you. So if you see this gray, now it is not the same as the red, which means that after applying the filters, the amplitudes have slightly changed. It has come down, both this positive, the negative peak has come down. Similarly, the positive peak also has come down in this case. But, okay, now you can see the effect of applying the filters. Let me just try to add the filters. On the left, also I wanted to show you, on the left bottom, you see the filter response. It starts almost close to 0, and from there on, gradually it weans over. Let me just edit the filter and increase this to 3 hertz or 3 hertz maybe. When I made the low cut of frequency close to the actual data frequency, which is around 5 hertz, now you can see the amplitude has really changed and there has been a shift in the data. But still, you can see that the what you call frequency response, still it's curved, almost having also, I mean, it gives almost a very good what you call a cutoff at around 5 hertz or 3 hertz. So if I apply 3 hertz as a cutoff frequency, it doesn't mean that it will actually cut off at that 3 hertz. There can be a slight amplification given to frequencies below 3 hertz and slightly after 3 hertz also. That is why you have this. So let me make it 5 now. At 5 hertz, we see that the amplitude has really suffered and the peak, if you can see, has moved towards the left. Here you can see the peak has moved towards the left. You can well appreciate it at the bottom. So doing this can change the waveform also. Now, if I want to be more, more kind of aggressive when I apply the filters, I need to be very sharp. What you call filter response, then I choose 12 decibel or else 48 for that matter, 48 dB. When if I'm very strict, now I have a very good, very aggressive, filtering. I did that at 5 hertz. It doesn't amplify anything below 5. If you look at here, you can see that the waveform has totally changed. Instead of this red waveform, we got we introduced multiple peaks, which means that we have distorted or else introduced artifacts. We have distorted the real waveform, and your results will definitely suffer if you do this. So again, when you change the filters to 0 phase, you can see, still it has come back, but the what you call amplitude has significantly suffered. At the same time, you also have introduced new phases. The number of phases has increased from the real and originally simulated data. So that said, let us try to change this back to 1 hertz, far away from the basics, from the frequency of interest, which is 5 hertz. This looks fairly good. Now I change the high pass filter to 10 hertz. Still the waveform has slightly moved, but not much. It has just slightly moved, but then we have not introduced any more factors to it. But when I change this high frequency close to this frequency of interest, 6 hertz, you can still see it has moved a lot. So the low frequency filters, when you apply, really affects this, and high frequency filters are not that much affecting. So the main takeaway message, what is shared here is, please ensure you give sufficient breathing space for the filters so that the filter limits don't really affect your data. So here we go. You can be more lenient here. This looks fairly good. So I think I have explained. So the takeaway message, which I wanted to share here is when you're applying filters, you need to ensure that the closer your frequency of, the closer your filters are at the frequency of interest, the greater the effect of the filter on your signal. So give some breathing space to the filters, and you need not be very aggressive to be the cutoff. You should give some space for the filters to have. Next is the filters will not only affect the frequencies, it will affect the amplitude. What we have seen just now, the filters can have a significant effect on the amplitude as well as the shape of the waveform, which we just saw. So as you change the filters, you can also introduce new waveforms to it. So we need to be super careful when we apply the filters. Always look at the frequency response curve wherein your frequency of interest is preserved. Next is low cutoff filters usually have, as we have seen, the low cutoff filters have a greater impact on the evoked potentials than high cutoff. When I changed the high frequency, it didn't change much. Instead, when I changed the low frequency filters, we saw how we introduced the lags as well as shift, as well as change in the morphology of the simulated signals. So if you are interested in evoked potentials, please play with the low frequency cutoff filters very carefully. So also, as discussed earlier, the application of a filter can lead to introduction to false components, which means that, as we have seen, there were no components earlier. However, when I introduced certain filters of a cutoff and I was aggressive about the filters, now you can see there is a gray waveforms. New waveforms has been introduced to the waveforms, new components. So if you are interested in, and again, another point is that if you are interested in early components which are less than 100 milliseconds, you should not use your lower cutoff filters that are zero phase. Because if you use that, you might project unintentionally the later components onto your signal. So with this, I want to ensure that you will use your filters appropriately.